We'll spend the remainder of this unit of study on work, energy, and power by investigating a few problems taken off of advanced placement exams. This first one from 1982 is a question that it's all about kinetic energy. We're told that a car with a mass of m is moving initially with a speed of v0 on straight horizontal road. The car is brought to rest so that the velocity as a function of time can be expressed as an equation of this form. So it's being brought to rest by a non-uniform acceleration. It's brought to rest by a force that is not constant. The only constant is the value of r in that expression. Part A, we need to develop an equation that expresses not so much the kinetic energy, but the time rate of change of kinetic energy. So we're really being asked for power, right? Power is the rate of change of energy. Okay, so let's see. First of all, let's answer this question by finding an expression for kinetic energy. So we know kinetic energy is defined as 1/2 mass times velocity squared. And notice I'm using capital M for mass just because that's how the problem set it up. Okay, so our kinetic energy is equal to 1/2 times mass. Well, knowing this formula, we can make a substitution. All right. If we distribute, we get kinetic energy is 1/2 m times v0 squared minus mRt over 2m. Oh, well, then the m cancels out. And since we're asked for power, or the time rate of change, we need to take the derivative with respect to time. But all of this is just a constant, so the derivative of that portion gives you a 0. And so what do we have as our final result here? We just get negative r over 2. All right. Part B, determine the time it takes to come to rest. Well, that just means the velocity has to be equal to 0, okay? But the formula we're given is v is the square root of v0 squared minus rt over m. So that just means all of this has to be equal to 0. Or in other words, v0 squared has to equal rt over m. So t is equal to v0 squared times m divided by r. So part A, negative r over 2. Our answer to part B, mv0 squared over r. Now part C, develop an equation for the acceleration as a function of time. Well, acceleration is just equal to the first derivative of velocity with respect to time. So our velocity is v0 squared minus rt over m to the 1/2 power. Another way of thinking of the square root. So dv dt is equal to 1/2 times v0 squared minus rt over m to the negative 1/2 multiplied by, notice we're just using the chain rule here, multiplied by negative r over m. Okay? Part D, sketch the magnitude of the braking force as a function of time. Well, force is equal to mass times acceleration. And we have the acceleration from our previous problem. So let's just write this a little more clearly. The force is equal to, how can we express this a little easier? Well, we have to multiply m times negative r divided by, let's see, we got a 2, an m, and then since this is to the negative 1/2 power, can't we write it like this? 2m times the square root of v naught squared minus RT over m. There we go. Oh, and then the m cancels out. So the force would be equal to negative r divided by 2 times the square root of v naught squared minus RT over m. But careful, the question asks for the magnitude. So in that regard, we can ignore the minus sign. All right. So if we need to graph it, let's just get a few data points. Let's see. We'll plug in values for t and see what we get for f. So first of all, let's plug in 0 for t. Okay, then this term here goes to 0, and the square root. Okay, so we're going to have the initial force is equal to r divided by 2v naught. And ultimately, we're not going to plug in any value of time greater than the value we found in our answer for part B, because by that time the car's been brought to a stop. So let's actually plug this value in for t and see what we get. M v naught squared over r. So let's let t equal m v naught squared over r. So if we plug that in for t, now we have r over 2 times the square root of v naught squared minus, minus v naught squared. This whole term is going to go to 0, and that's in the denominator. So that means the force is going to blow up to some infinite value at that point. That means on our graph, on the axes, this time t, which we know is the same thing as m v naught squared over r, that becomes a vertical asymptote. The initial force is not 0. The initial force we found here in our data table, it's equal to r divided by 2v naught. So we can plot that point here. Call that f naught. So somehow we have this data point and then at this value of time approaching infinity. So we actually probably don't need to fill out any other values in our data table. Doesn't matter. We can get a sense of what the graph's going to look like. I think I can do better than that. So it's got to sharply curve and head toward an infinite value. Okay, so there we have it. That's the 1982 number 2 problem from the Level C AP Physics exam. Thanks for watching.